All right, let's go over some more differentiation rules. Let f of x and g of x be differentiable where c, m, and b are constants. So we just talked about the power rule on the other side, but I'm just wanting to sum it up here so you guys have something to go through. So the power rule was when we had d over dx of x to the n equals n times x to the n minus 1. That constant rule, so if you take the derivative of a constant, oops, I was getting ahead of myself there, it is just 0. All right, let's learn some new ones. So the derivative of an exponential function. So d over dx of e to the x is just e to the x. The constant multiple rule. So what this means is if you have a constant that is getting multiplied to a function and you're taking the derivative of that whole thing, we can actually pull that constant out in front. The sum rule is if you're adding two functions together, you can just take the derivative of the first function plus the derivative of the second function. And you'll see why this comes into play and makes our lives a little bit easier with some more complicated functions. And then the sum rule or the difference rule is the same thing. If you're subtracting two functions, you can just take, and you're taking the derivative of that, you can take the derivative of the first function and then subtract the derivative of the second function from it. All right, so let's look at some examples of this. So find the first derivative formula for the following. So if I were looking at letter A, all right, this is using that exponential rule. So the derivative of an exponent or of the exponential function is just e to the x. All right, letter B. So here, this is going to be using that formula d over dx of a constant times a function. Means I can pull that constant in front and just find the derivative of that function. Okay, so if I were to look at this one, we would have d over dx of 7x squared equals, I can pull that 7 in front and find the derivative of x squared. So because we actually have a formula for x squared, we don't have a formula for something getting multiplied by x squared. So I can use that power rule now, so that 2 comes down, and then we are going to subtract 1 from the exponent, so that's going to give me 14x to the first power. So here's where the difference in sum formulas come into play. So what those will tell us is that I can actually take this and just do the derivative of each piece separately. All right, so here, if I'm looking at this first one, this is going to be using that power rule. So the 2 comes down and then we subtract 1 from the exponent. 2 minus 1 is 1. Here I can use this constant rule. So I'm going to move that 4 in front and then I'll find the derivative of x. And then in this case, the derivative of a constant, because it's just 1, is 0. So that's going to give us 2x minus 4 times. So the derivative of x, move this power in front, so that would be 1 times x to the 1 minus 1. So that's going to give us 4 times x to the 0 power. We just to recall when we learned previously about exponents, anything x to the 0 power is just 1. So this is the same thing as 4 times 1, which is just 4. All right, let's keep on going. All right, if we have letter A and we had to find the derivative of this. So again, I'm going to go through and do, because this is the sum of two functions, I'm going to distribute that through. Okay, now I need to just kind of separate these. So it's like I'm doing multiple problems within run. So the first thing I'm going to do is I'm going to pull that 3 out in front of the derivative function, or the derivative thing to do. Derivatizer, we'll call it that. Okay, I'm going to pull that 4 out in front as well. And now I'm getting to actual things that I can find the derivatives of. So the derivative of e to the x is e to the x To take the derivative of this function, I need to first get it in terms of a power. So this is like x to the first power. So this would be 1 over x to the 1/3 power. And then I can move that 1/3 up, and that would be x to the negative 1/3. Now this is in a form that I can actually take the derivative of. So we're going to take that power, move it down in front. So that's going to be negative 1/3 times x to the negative 1/3 minus 1. So that gives me 3e to the x plus 4 times negative 1/3 x to the negative 4/3. So continue to go through and simplify this. All right, so that's 4 times negative 1 over 3x to the 4/3. Bring that inside. 3e to the x plus 4 times negative 1 over 3 to the x to the 4th power, and you're taking the cube root of that. Now I can just multiply that 4 through, like it's 4 over 1, so 3e to the x plus, actually it's going to be minus, because 4 times negative 1 is negative 4, so minus 4 over 3 times the cube root of x to the 4th. Okay, let's look at letter B. So letter B does not have it, we're not in a form that we can find the derivative of right now. We don't have anything for the derivative of f of x divided by g of x yet, but we will. But you don't even want to use that formula anyways on this, because there's a way simpler way to do this. So what I can do is, this just means take this entire quantity and divide it by this. So let's rewrite that. So I'm going to be dividing each of those terms, by t squared. So let's just do that. So these are equivalent statements. So now that I have this, let's just simplify it out. So derivative with respect to t of 1 minus 3 over t plus 1 over t squared. Each of these I can put in a way that I can actually find the derivative of. I have a rule for it. So let's go through and apply that derivative to each one of these. All right, so derivative of 1 is just 0. I can pull this 3 out in front, and I have d over dt of 1 over t. I'm going to keep this here, and then we'll kind of do all these things together. All right, so now let's rewrite this. So I've got it as a power, so that's going to be t to the negative 1. And then this one's going to be like t to the negative 2. Now I can apply that power rule. I don't need to keep on writing 0, so I'm just going to not write the 0 anymore. So negative 3 times. So now I'm going to take the derivative. So that d over dt goes away because I'm taking the derivative of it. So that becomes negative 1 times t to the negative 1 minus 1, which is negative 2. And then plus negative 2 times t to the negative 2 minus 1, which is negative 3. So that's going to give me 3 over t squared minus 2 over t cubed. All right, let's go back to this problem that we have used so many times in different examples. A ball is launched vertically into the air from the ground with an initial velocity of 96 feet per second. Its height, s of t in feet, as a function of time, t in seconds, is given by s of t equals 96t minus 16t squared. Find s prime of t and s double prime of t, so the first derivative and the second derivative, and interpret it with units. Okay, so that first derivative, which is that velocity function, so that's now, instead of having to do the long way to find that derivative, which we've done, and it took a while, we can use our nice little formulas now. All right, so we get taking the derivative of this function. So that's going to give us d over dt of 96t minus the derivative with respect to t of 16t squared. So I can move that 96 out in front. Taking that derivative with respect to t, I can move that 16 out in front with respect to t squared. So that's going to give me 96 times So this is like to the first power, so 1 times t to the 0, which is just 1, minus 16 times the derivative of t squared is 2 times t to the 2 minus 1, which is 1. So that becomes 96 minus 32t. So this is the velocity function. Remember, the derivative of the displacement is velocity. And those units, so again, this is finding that slope. So the change in y was the change in height. So that's going to be feet per change in x. And the x values were, our t values are given by second. So feet per second. If we were to find that second derivative, it's finding the derivative of the first derivative. So that's going to be finding the derivative of 96 minus 32t. So again, it's finding the derivative of the first derivative, which we found right here. So that gives us 96 minus the derivative with respect to t of 32t. So the derivative of a constant is 0. I can move that 32 out. And the derivative of t is just 1. So I get 0 minus 32, which is negative 32. In terms of units, it's going to be taking, again, that change in y over change in x. So the change in y is going to be the feet per second. Change in x, which in this case is our input values, in this case is t, is over seconds. So it's negative 32 feet per second squared. Again, that second derivative of the displacement function is, or position function, is acceleration. So the first derivative is velocity, second derivative is acceleration. So if I were to find what's the acceleration at 2 seconds, well, that would be substituting 2 into that acceleration function, which I found was negative 32 feet per second squared. So that means no matter what the time is, the acceleration is always the same. This ball is always going down. So we would say that our acceleration, the answer to that would be negative 32 feet per second.